Welcome. We're going to be, as you can see, talking about inverse trigonometric functions. And before we do that, let's go back and kind of review what we know about trigonometric functions. And this is really kind of important here. If we think of a trig function as a factory, much like a Keebler-Cookie elf tree, product gets delivered to a factory, and the factory does something with the product. And mathematically speaking, in terms of function, we want to know what's actually being delivered, what is going into this function. And into a trig function, typically we'd say things like sine of 30 degrees or cosine of pi on 4. What we're putting into it are angle measures. And then what come out of it? Well, sine, SOHCAHTOA, opposite on hypotenuse, or in terms of x's, y's, and r's, tangent, y on x. We're getting out ratios, fractions, of side lengths of the triangles that are produced. So what comes out is ratios of the side lengths produced by the angle measure. Now in this case, the ratio of the side lengths is a function of the angle measure. So let's talk about inverse trig functions then. Of course, what must go into an inverse trig function if it's going to undo the job that the trig function just went into? We need to put in ratios of side lengths. So when I see something like tangent inverse of 2, I don't like it. 2 is not a ratio. I want to think of that in terms of the tangent y on x or opposite on hypotenuse ratio. I want to think of that as tangent of 2 on 1. Oh, the opposite is 2 when the adjacent is 1. Opposite on adjacent, tangent. So let's move on. Ratio of side lengths get turned into angle measures. Okay, this screen I want to talk about our all students take calculus. In other words, all trig functions are positive here, sine is positive here, tangent is positive here, and cosine is positive here. Now, we know that a sine graph, I'll fit that in up here, looks like this on and on and on and on, dot, 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 dot. And to have an inverse function, your original function, to have like an inverse sine function, the original sine function has to be 1 to 1, and this is most definitely not 1 to 1. So what we have to do is we have to lop that function off. We have to look at a portion of it where it's 1 to 1. For instance, I could say, well, let's look at this portion here, and let's look at this portion here. If I just look at those two portions, those are all the possible y values of this, and no repeats. Okay, well, that's not the choice that we're going to lop off parts of the graph. It's not going to be that. So here's the deal on it. If this is a rotation of 0, we will always go from 0 to 90 or to pi over 2 to get our positive value. So sine inverse will include 0 to pi on 2. That gets me all the possible, that would be rotationally speaking, I'll go in green here, from here to here. Okay? Now, I don't want to continue into quadrant 2 because into quadrant 2 I have positive values that start decreasing, as we can see on this graph right here. So quadrant 2 is off limits, otherwise my function's not 1 to 1. But I need to pick up some negative values. Well, sine is negative in quadrant 3 and quadrant 4, so I have a choice between those two. Here is so our first criteria is we want to stay as close to 0 as we can. And because that's our first criteria of it, my choice being quadrants 3 or quadrants 4, quadrant 4 is close to 0. Back up at the graph, if we look at that, that would include this. This is negative pi on 2 right here to pi on 2, much as this is negative pi on 2 to pi on 2. So sine inverse is bound to return answers between negative pi on 2 up to pi on 2. Okay, well, it'd be nice if all of them were that way. So let's take a look. Let's talk about cosine for a moment. Take a look at the cosine graph up top here. So here's our cosine graph. It looks like This looks a lot like the sine graph, but it starts up top. It starts at 1. It starts at a peak. And it's not 1 to 1, as we can see. A horizontal line would go through many points on there. So cosine graph, again, the positives we're going to take from quadrant 1. The negatives, if I try to move back into quadrant 4, as you can see up here, so far we've taken these values. Those are our quadrant 1 values, 0 to pi on 2. If we try to take these values, we're repeating positive. We can't go back into quadrant 4. We can move forward, though, into quadrant 2. This is where the cosine inverse is going to pick up negatives. Okay, so that's through pi, 0 to 180. So cosine inverse is bound to return values between 0, and pi. How about tangent inverse? Well, tangent inverse, once again, we're going to use the positives here for our positives. Tangent inverse, where is tangent negative? Tangent is negative here and here. And here's the convention for this, I believe. Somewhere along the line, I don't know if this is accurate history or not, somebody got to decide what portions of the graph we're looking at. And I believe this was kind of the thought. Let's stay as close to 0 as we can, giving preference to quadrant 2 and 1 over quadrants 3 and 4. And let's go positive when we're given an option. And if we're given an option, in this case, to go positive or stay close to 0, if we stay close to 0, we are going in a negative direction close to 0 versus the long positive direction, if that makes sense. You might need to replay that one. But tangent inverse, like sine, is going to return values between negative pi on 2 to pi on 2. And we're going to talk a lot about that. That is a big portion of what's going on in this assignment. In fact, if I could say 2 things about this assignment, it is trig inverse functions want ratios put in them, ratios of side lengths of right triangles, and we need to make certain that we're building triangles in the correct quadrant, close to 0 as we can. If given an option, we're going to choose to go in a positive direction, and you'll see examples of those that I think will help clear up what we've just talked about. Okay, so cosine inverse of. What I like about this is I like this as a fraction. This is the ratio x to r. It's the cosine ratio x to r. X is in ratio to r root 2 to 2. However, you might recognize that as the rationalized version of this. And that those are the values I'm going to choose to build my triangle with. All right, now all students take calculus. I need cosine like cosine of theta. I need cosine of theta to be negative. What quadrant am I going to go in? I have a choice between this quadrant and this quadrant. Should I go this direction, or should I go into quadrant 4? Given the option, we're going to go positive versus negative. So I'm going to build an x on r of negative 1 to root 2. And you would recognize that then as a 45, 45 right there. So the angle we are looking for is this angle between 0 and pi that produced this. Well, that is 135 degrees, or steps of 45, 1, 2, 3 steps of 45, pi on 4 being 45. Okay. So those are our options. I believe our book right now is focusing on radians, but either of those are options depending on what type of answer you're looking for, radians or degrees. Again, what goes into a trig function, a ratio, what comes out, a degree, or not a degree measure, but an angle measure. All right, let's move on. Tangent inverse of root 3. Ooh, I don't like that. What goes into trig inverse functions? Ratios. Oh, now I feel better. What ratio is tangent? Y to x. Y to x, root 3 to 1. What quadrant am I going to build that triangle in? Because it's positive, all positive inverse functions go to first quadrant between 0 and 90 or 0 and pi. So y root 3, relatively long, compared to relatively short x. Oh, that's a 60-degree angle. There's my rotation. I put in a ratio. I get out an angle measure, 60 degrees, or 1, that's 2, 3 steps, just one step of 60 degrees, pi on 3. So that one really focused kind of on both aspects of this lesson. We need to put in ratios into trig functions, and we need to get out degree measures. And then the second is, what quadrant do we build the triangle in? When it's an inverse function of a positive value, they're all quadrant 1. Okay, write theta as a function of x, which means basically I want theta equals something. You could write it as theta on x, or theta of x equals, but I want theta alone. Now, you may not be thinking in inverse trig functions yet, but if you saw this, I would think immediately you would say, oh, opposite adjacent, I know something about those in terms of theta. Opposite adjacent, I know that tangent of theta is x plus 1 on 10. But I want to get rid of tangent. You cannot divide tangent. It is not tangent times theta, it's tangent of theta. We have to undo the tangent factory. To undo the tangent factory, we use the inverse tangent factory. So I would take inverse tangent of both sides, and I end up with the tangent inverse cancels tangent. I get theta equals tangent inverse of x plus 1 on 10. Now theta is a function of x. In other words, I put x into this factory and I get out theta. So you could write it theta of x. Okay. Now maybe we'll do that in one step soon as we start thinking more in terms of inverse functions. All right, same problem, but now we're supposed to use all 3 inverse trig functions. So they're talking about sine inverse, cosine inverse, tangent inverse. From theta, I've got the opposite. I've got the the hypotenuse. Excuse me. That sounds like sine. Sine of theta equals opposite x on hypotenuse 3. Therefore, sine inverse, undo it. We turn theta into x on 3. We have to turn x on 3 back into theta. Okay, take the sine of both sides. I probably should have written that backwards. I'll fix that on the next one. Now, how about talking about cosine of theta? For cosine of theta, I need the adjacent side. That's a little Pythagorean work. So I'm going to square the hypotenuse, 9, minus square the other side, x squared. Take the square root of that. Basically, if I called this side a, I would have 3 squared equals x squared plus a squared. Solving for a, I think you can quickly see we get to that point. So cosine of theta is adjacent root 9 minus x squared on hypotenuse 3, making theta cosine inverse of 9 minus x squared's root on 3. How about tangent? Tangent of theta is opposite x on adjacent, square root 9 minus x squared, making theta equal to tangent inverse of x on square root of 9 minus x squared. I had a student ask, can we go to that directly? And I said, yes, that's the goal. We're thinking in terms of tangent inverse functions. I'm not certain everybody's there yet. Okay, let's check the next problem. Oh, this is a fail problem for some people, because if you're well versed, at least in this course, you would recognize this is a problem where I have a function of an inverse function or an inverse function of a function. I'm just going to end up with 7/2 pi. Boy, it seems like it. 7/2 pi. 1/2, 2, 3, 4, 5, 6, 7 gets me to right there. Remember, cosine inverse is only allowed to return values between 0 and pi, and 7/2 pi is most certainly not between 0 and pi. So, if I go to my original angle right here, I could call this the point 0, -1, r is 1, this is x, this is y, and cosine x on r, 0 on 1, this whole thing is 0 on 1. I want cosine inverse of 0 on 1. I could write 0, but I like this guy to be a ratio. So where along here is x 0? X is 0 and there is no right-left movement. X is 0 here. That is a rotation of pi on 2. Pi on 2 or 90 degrees, but there certainly seems some merit in answering in terms of radians here when we started with radians. We'll take a look at some more like that. But that one's a trick problem in some respects because it's so tempting just to say 7/2 pi, but we need to remember cosine inverse 0 to 180, 0 to pi has to be in there somewhere. Okay, tangent 3/4 pi we're going to start with. We're not dealing with tangent inverse, so I'm going to build a triangle. 3/4 pi, that is 3 rotations of 45 degrees. 1, 2, 3, getting me right here. I could call this 1 and root 2, provided I account for the negative, because that is to the left. So this is cosine inverse of, I need tangent from that triangle, y on x, -1. This is a big yuck right here, though. I don't want to put just plain old numbers into cosine inverse functions. These are supposed to be ratios. So cosine is the ratio x on r, which means x has to be -1 when r is 1, because r can't be negative. When does that happen? Along here, because that's my only possibilities for cosine inverse. This point right here would be -1, 0, and r is 1, so x on r, that's it. Since we started in terms of pi, I'm going to answer in terms of pi, in this case, just 1 pi. This would probably be a good point to pause and try this one at home if you like, and then I'll come right back and do it. Okay, if you paused, welcome back. If you're just following along, great. Into tangent inverse, I want to put ratios. So I need a y on x, that's tangent. I need a tangent ratio, y on x, to be equal to -1 on 1. When can tangent be negative? Tangent can be negative here or here. What's our convention say, though? We want to, first case, we want to stay as close to 0 as we can, then choose positive over negative. Well, I'm choosing negative because that's as close to 0. So tangent inverse returns values along here. So I need a -1 to 1 here, making y be the negative, x is positive to the right. This is root 2, so here's a 45-degree angle this way. This might as well have said then, what is sine of 45 degrees? That's the angle where tangent is -1 on 1 in the fourth quadrant, -45 degrees, excuse me. So sine from that triangle created is y on r, -1 on root 2. Or if you just can't stand it and need to rationalize, negative root 2 on 2. So build the triangle, put it in the correct quadrant. Let's think in terms of ratios going into trig functions. So this looks like a mess, but I like it in respect of it's an inverse function. I want a ratio. Again, tangent negative. Tangent could be negative here or here, but we're going to stay close to 0. That's our first choice. So that is y on x of 12 to 5. We pick up the negative here because, of course, that's down. Pythagorean work gives me 13 here. The radius is always positive. And the cosecant ratio, sine is y on r, so this is r on y. I want r on y of this angle. R on y, 13 on -12. So it's just another disguised way of the author just having us build triangles, do some Pythagorean work, come up with some trig functions. How about this guy? Secant of sine inverse of x minus 1. Not only is this kind of yuck, because there's a variable here, but it's definitely yuck because I want it to be a ratio. Oh, okay, so my y on r ratio is in x minus 1 to 1. Why in the first quadrant? Well, I don't know whether x minus 1 on 1 is positive or negative, so I just hope it works out if I put it in the first quadrant. Okay, now for secant reciprocal of cosine x on r, I need the r on x from this triangle, which means I do need to find my x value along here. So I'm going to do some Pythagorean work. That would be 1 squared hypotenuse squared minus one of the short sides, x minus 1 squared, square root equals the other short side if I call that a. I didn't want to call it x, I think, for obvious reasons. Okay, if I do a little simplifying here, this gives me 1 minus FOIL, x squared minus 2x plus 1, and distribute the negative, and I get square root 1 eventually is going to be minus 1, so I get a negative x squared and eventually a plus 2x. So this is root negative x squared plus 2x. And what am I looking for? My r value on my x value. Okay, so that is it. A little trickier, not too bad though. And that is our book assignment. If you're not playing along with our course, good luck to you as well. Hope this was helpful, and stay tuned.